Students, welcome to the second video in topic 5.4. We've talked about magnets. We defined what a magnet is. We talked about poles and forces and magnetic field patterns. So what we're going to do is we're going to get into the sort of nitty-gritty of how to quantify how moving charges behave when they enter magnetic fields. And I'm going to introduce to you something called the right-hand rule. Now, remember we talked about this sort of thumb rule where if we have a current carrying wire and your thumb is pointed in the direction of the current, your other fingers curl around to show you the circular nature of the magnetic field that's created by the moving charge in that current, okay? So I'm going to show you another rule with your right hand. It's called the right-hand rule. Now, in order for a charge to experience a force in a magnetic field, okay, remember that it must be moving. And it turns out that the velocity of the moving charge must have a component that is perpendicular to the direction of the B field, okay? This is crucial. If it's parallel, if the velocity is parallel to the field, there will be no magnetic force that acts on that moving charge, okay? Now, if you've taken higher level math and you've studied dot and cross products of vectors, this should remind you of what's called the cross product, okay? I'll talk a little bit more about that. Now, in other words, you have a magnetic field that in this case is pointed to the right. Okay, if your velocity vector is either pointed perfectly to the right or perfectly to the left, okay, that is to say if the angle between V and B is 0, then you would have no force acting on that little positive test charge Q naught, okay? The maximum force would be acting on it if it were at an angle of pi over 2 to the B field, or in other words, the V and B would be orthogonal. Now, if it's some other intermediate angle, then the force would be between the maximum magnetic force and 0, okay? Note that the direction of the force on Q naught would be upward in both diagrams, okay? You see how this F max is upward and this F is upward? That's an application of the right-hand rule, which I'm about to explain to you. Also note that the angle theta determines the magnitude of F, and that theta can be altered by changing either V or B, right? You can either change the velocity or the magnetic field in order to change that angle of theta, okay? All right, all three of these vectors, V, B, and F, can be related by what's called the right-hand rule, okay? And the right-hand rule is this, okay? If you take your right hand, your thumb points in the direction of the velocity vector, your index finger points in the direction of the B field, and your middle finger or your palm, however you want to do it, in this case it's just coming out of your palm, that indicates the direction of the magnetic force on a positive particle, on a positive charge moving in a B field, okay? Now, if it's negative, there are two things you can do. Number one, you can use your left hand with exactly the same rule, V, B, and F, or, and this I don't hardly ever use my left hand for the right-hand rule, I end up using my right hand, noting that for a negative charge, okay, or negative current, okay, the magnetic force would actually be coming out of the back of your hand. Now, if you're double jointed, you could also just take your middle finger and put it back like that, so that they're all orthogonal for a negative charge, but that might actually hurt you, and I don't want you to hurt your middle finger, okay? All right, so again, V, B, and F, okay? That's called the right-hand rule, and you're going to be using this. Don't be afraid to use your right hand when you're solving all these problems, okay? If the charge is negative, F is in the opposite direction, pointing out of the back of the hand, and the thumb often points in the direction of the true current, not the conventional current, okay? Because V is in the same direction as I, okay? All right, so let's do a couple of examples here, all right? So, number one, an electron approaches a bar magnet as shown. Does the electron experience a force? And of course, the second is going to say, well, would a positive charge experience a force? And if so, in what direction? Well, you have to figure out in what direction the B field is in this case. Now, because the North Pole's over here and the South Pole's here, it makes sense that the B field goes like this, and it's in this direction. So exactly where the electron is located, the B field is pointed to the left. Okay, so this is V. So using your right hand, you have V is up, okay? B is to the left, and the force is not coming out of your hand, but out of the back of your hand, and it would be into the page, into the plane of the board in this case. Now, the positive charge would just be opposite, out of the page. And we would show it, for part A, we'd show it by an X, we'd show the force by an X, and for part B, we'd show it by a dot, okay? That's how we would do that three-dimensionally. Okay, example 2. A velocity selector is a device for measuring the velocity of a charged particle. The device operates by applying electric and magnetic forces to the particle in such a way that these forces balance. What should the charges be on the plate such that the positive charge pictured travels in a straight line through the tube? Okay, think about it. Now, using your right hand, let me see your thumb in the direction of the velocity. Okay, your index finger, that's B field, is into the page. It's a positive charge. So as a result of the B field, the force on the charge would be upward, right? There's going to be a force acting upward. Now, so what you need in order for the charge to go through that tube undeflected, you need the electric field to be downwards, and it has to be the same magnitude as the magnetic force acting upwards. The only way this is going to happen is if you have a negative plate on the bottom and a positive on the top. So again, without the charge plates, the charge would go upwards, right? It would go upwards and it would hit the top of the tube. Because there's a negative plate on the bottom and a positive on the top, it's being pulled downwards or pushed downwards. And if you balance them just right, it will go right through that tube undeflected. That is cool, okay? Okay. Remember when we defined the electric field, we said the electric field was the force per unit charge on a small test charge, such that E is F over Q naught. Now, in a similar fashion, the B field is defined as the force on a small test charge placed in that B field. However, it's more complicated because you know that charge has to be moving in order for that force to even exist. So this velocity must be accounted for. Specifically, as we talked about before, only the component of V that's at pi over 2 to the B field contributes to the F, okay? So really, the definition of our B field should be the force over the charge times the component of V, which is parallel or perpendicular to B. Now, this, as I said before, if you're in higher level math, this should remind you of something called the cross product. And what the cross product is it's a vector operation that ensures that two things. Number one, the product is itself a vector, and number two, that you're actually multiplying the perpendicular components of two vectors together. More generally, and this is how you see it written, F equals QVB sine theta, or QV cross B, okay? This is how you see it in your data booklet. Now, theta here is the angle between V and B. So you can see that if everything is orthogonal, in other words, if V and B are at right angles to one another, of course, the sine of pi over 2 would be 1, and it would just be F equals QBB. And in almost all circumstances when you're solving IB problems, that's going to be the case, where you don't really have to deal with an angle theta, okay? So it's just F equals QBB. They are all vectors. Be very careful working with this equation when we're dealing with magnitudes and directions of these quantities, okay? Okay, now the force on a charged particle moving through an E field is very different than the force acting on a charged particle through a B field. We just did that example where we had the positive and negative plates in the B field, and we saw how you'd have to orient those plates in order for the charge to not be deflected, okay? This is so cool, and it's so important that you understand this difference, okay? A charge going through an electric field moves in a parabolic fashion, and that's because you have a constant force acting in one direction. It's exactly the case of kicking a ball off a cliff. You have the weight or the gravitational force constantly acting on the ball. Therefore, it's accelerating, and it moves in a parabolic fashion. That's exactly how charges move through electric fields. The path is parabolic, there's a constant force, and that means we can use the equations of motion for constant acceleration, all right, from our kinematics unit. Now, it turns out that moving charges do not move in a parabolic fashion through magnetic fields, okay? And the reason is because the force does not remain constant. The magnitude remains constant, but the direction of the force as a vector constantly changes. And it's always pointed towards one particular spot. And what that means is that it moves in a circular path. So it's a circle versus a parabola. It's absolutely crucial for you to understand that, okay? Path is often actually a spiral, but when we're doing problem solving, we still treat it circularly. And what that means is that we use the old centripetal force equation, and we equate that to the magnetic force, and I'll do a couple of examples of that in just a little bit. The force really is the centripetal force, okay? So let's do an example, okay? A proton in a particle accelerator has a speed of 5 × 10⁶ meters per second. The proton encounters a magnetic field whose magnitude is 0.4 Tesla and whose direction makes an angle of 30 degrees with respect to the proton's velocity. Magnetic force on the proton, that's easy, right? That's QVB sine theta. Just plug in your numbers, and you need to realize that it acts upwards using your right hand, okay, because it's a positive charge, it's a proton, it's going to act upwards as shown in the diagram. Acceleration, F equals ma. Solve for A. Super simple, right? 9.6 times 10 to the 13 meters per second squared, which means that it's not going to accelerate for very long unless, because then it would exceed the speed of light, which is not possible. Now, what would be the force and acceleration if the particle were an electron instead of a proton? Everything would be the same, okay, in terms of the force, but it would be downward, okay, in the opposite direction, and also the acceleration would be different because remember the mass of an electron is much, much smaller than that of a proton, and so its acceleration would be much greater as a result of Newton's second law, okay? All right, so again, circular motion. Turns out that a moving charge in a magnetic field moves in a circle, okay, and you can use your right hand to figure out that a positive charge, right? Everywhere on this diagram, you see that that force, which is coming out of the palm of your hand, is going towards the center of that circle, okay? So in this case, the centripetal force is exactly equal to the magnetic force. In other words, mv squared over r equals qvb because everything's orthogonal. And if we want to find the radius of the circle that the particle moves in, all we do is we just rearrange this equation for r. Notice that one of the v's cancels out. You end up with a 1 up here on top of this v, and you end up with r equals mv over qb, okay? You often see, remember I said that often it's a spiral. We'll talk a little bit more about this. These are particle tracks in what's called the bubble chamber. So what scientists do is they shoot these high-speed particles into these chambers, and they watch and they see the patterns that they make. There's a B field in the chamber, and they can study the path of these high-speed particles and determine things like their velocity, their mass, whatever, given one thing or the other, okay? Pretty cool stuff, all right? Now, there's an application of this, and it's called a mass spectrometer. And mass spectrometers are used to determine the relative masses and abundances of atomic isotopes, okay? And remember what an isotope is, right? And different isotopes of the same atom are different sort of versions of that atom that have the same number of protons in the nucleus, but different numbers of neutrons, and therefore different masses, right? Okay? Now, so what you do is you take a... You take a sample of atoms or molecules and you ionize them, meaning that you're stripping off the electrons, okay? All right, the electrons then go through this metal plate into a region of a B field. In this case, it's out of the plane of the paper. The ionization removes one electron from the particle, leaving it with a net positive charge of QE, okay? The positive ions are accelerated through a potential difference right here between these plates, okay? With a particular speed v, the ions enter through the plates and enter this region of the constant B field, and they're deflected in semicircular paths, okay? Now, only those ions following a path with the proper radius strike this detector over here, which has a very small opening. And that records the rate of the arriving ions. Now, for the ion, it turns out that because of conservation of energy, its kinetic energy that it gains is equal to the change in electric potential energy over here. So we can figure out what the initial speed and, of course, the initial velocity in this case is straight up perpendicular to the field. V in this case is the square root of 2q times the potential difference between the plates over the mass of the ion, okay? Now, I can then, noting that R equals mv over qb, I can then solve for V. V equals R qb over m, and if I combine equations 1 and 2, I can eliminate the velocity, and I can figure out what the mass of that ion is, what that particle is that goes into that B field. Pretty cool. Now, by experimentally changing B while keeping Q, R, and V constant allows different masses to enter the detector. And if you graph the abundance against B squared, or the number of arriving ions against B squared, it gives you an idea of what masses are present and how many of them there are in the sample, okay? Now, the mass spectrometer is a really interesting thing. You may be asked questions about it on the IB, but they're not going to be super complicated. This is more for just for you to understand that there are many important applications of B fields and moving charges, and this is just one of many of them. But you should be familiar with this derivation of this equation and understand generally how a mass spectrometer works. Okay. All right. Let's do an example. This last example for this video. Okay, these are particles in a bubble chamber. Okay. The figure shows a bubble chamber tracks resulting from an event that begins at point A. Okay. At this point, a gamma ray. Okay. Don't worry so much about what a gamma ray or radioactivity at this point. Traveling in from the left spontaneously transforms into two charged particles. There's no track from the gamma ray itself, which is why you suddenly have this place in space where you have the beginning of 3 different tracks. These particles move away from point A, producing the 2 spiral tracks. A third charged particle is knocked out of a hydrogen atom and moves forward, producing the long track with the slight upward curvature. Each of the 3 particles has the same mass and carries a charge of the same magnitude. There's a uniform magnetic field out of the paper towards you. What are the relative speeds and the charge carried by each particle? Very interesting, okay? All right. Turns out that particle 1 has to be negative. Well, why is that? Because there's an upward track. Its force is acting upwards and into the center. Let me get my pen here. There's a force acting upwards into the center of this spiral of this circle right here. Okay. Now particle 2, and that's an application of the right-hand rule. Particle 2 is positive because it's in the opposite direction. Okay, right towards the center of that circle. Okay. Downward track indicates a positive charge in this case. And particle 3 would also be negative because you see that there is a force that is actually pulling it upwards in the same direction as particle 1. So particle 1 negative, particle 2 positive, particle 3 negative, okay? Now what about the speeds, relative speeds, okay? Turns out that the one that's going the fastest is the one with the tightest spiral, okay? As a result of our equation relating centripetal force and magnetic force. The one that's the slowest is the one that has the largest radius, and that's V3. So V1 is greater than V2, which is greater than V3, and this is really cool stuff.